What's up, everybody? Welcome to lecture 21 of Trig. Today we're going to be talking about the remainder of section 3.4. But to start with, I thought we'd look at a little bit of what we did last class. Last class we were talking about projections. In this image, what we've got is a projection of u onto the vector v. And we call that projection w1. And from it, we find another vector, w2. So what is all of this? Well, we got this vector u, right? And we're going to imagine casting a light, or shining a light onto u at a right angle, to v. Well, that means u is going to cast a shadow onto v, right? And because it's casting a shadow onto v, we can think of u having some component part in the direction of v. Well, we call that component part w1. And the part that's missing, the part that when added to w1 gives us u, well, we're going to call that part w2, and it's going to be orthogonal to w1. So in this way, we can decompose our vector u into two orthogonal vectors, w1 and w2. And that first part, w1, like I said, can be thought of in some ways as kind of a shadow being cast by u onto v. And w2 will be the vector in the direction that the light is shining. So you might be asking yourself, okay, what is this for? What can I do with this? Well, one thing we can do with this is calculate the work done by a force along some distance. So, work, as I've described here, is done by a force over some distance along some vector, and it's calculated in one of these two different ways. Work is either the magnitude of the projection of F onto u times the magnitude of u, or you can calculate it with the dot product of force and the distance. Okay. Or force and the vector, I mean to say. Okay, so as an example, because what the hell, right? As an example, let's consider this. What we've got in this picture is a little red wagon cart being pulled. Now notice when you're pulling in that little red wagon cart, the direction of the force that's being applied to it is in the direction of the handle, right? So our force in this case is along our little handlebar, and it's the vector 3, 2. Okay. Now having said that, we're going to pull our cart. A distance of 5 along the x direction. We want to know in this diagram, in this picture, in this graphical representation, how much work's being done. Well, to do that, we can apply one of these two formulas, right? So, I think looking at this second formula is going to be that fast, right? So let's go ahead and do it. What we've got is F dot U, which is equal to 3, 2 dot 5, 0. This is going to give us 15, isn't it? Okay. So this is 15. Now, I want to compare this to the other method because I'm not convinced looking at this that F dot U is going to be equal to the projection of the magnitude of the projection of F onto U times the magnitude of U. I'm not convinced that these two things are going to be equal, so let's check that really quick. What we've got is the magnitude of the projection of F onto U times the magnitude of U. Well, I'm going to calculate this part first, and I'm going to calculate it over here. Calculate it here, just so we can actually break out the math and see everything a little bit more clearly. All right. Where did my eraser go? My eraser's over here. All right, so the projection of F onto U is equal to F dot U divided by the quantity, or I mean the magnitude of U squared times the vector U. All right, so that means we've got F dot U. Didn't we already calculate that? That was 15. Okay. And the magnitude of U squared times U. Why am I rewriting this? Let me actually just write it out in component form. We got 3, 2, dot 5, 0 over the magnitude of 5, 0 squared times 5, 0. Okay, so what this is going to come out to be then is 15 divided 25 times 5, 0, which is going to give us 3, 5, right? I mean 3, 0. So this is the magnitude of the vector 3, 0 times the magnitude of the vector 5, 0, which is just going to be 3 times 5, or 15. So they come out to be the same. These things are equivalent. Well, that's convenient. So let's look at another example now. Let's see if we can better understand this with something else. How else we might use it. Okay, so in this question we've got two different things going on. One of the things we want to find is how much work has to be done, or I mean how far our object has to slide down or up the hill in order for its work to be equal to 3,000. The other thing we want to find out is how much force needs to be applied to hold it into place. Now, I know you're probably looking at this like, dude, this isn't physics class. Why are we doing this? You're right, it's not physics class, and I'm not going to get into the physics of it. But I'm going to tell you what it is we need to calculate. So for the first part of this question, we need to find out what the work has to be, how far it has to go in order for the work to be 3,000, right? Well, we know that the distance is going to be along V. So all we need to do is find out what the magnitude of that distance is, right? We don't need to find the vector, we need to find the magnitude. The other thing, to find out how much force it's going to take to hold that cart in place, what we're looking for is a vector of equal magnitude, but in the opposite direction of F1. Now notice F1 is the projection of F onto V. Okay, so how are we going to do this? What are we going to do? The first thing we're going to do is actually solve the second part. We're going to solve the second part because all it looks for is the negative of F1. We're going to need F1 to solve the first part. So let's go there. Well, we know that F is equal to the vector 0, negative 200. And we know V is equal to cosine 30, sine 30. Which is equal to the square root of 3 over 2, comma 1 over 2. Let's just go ahead and write that out. We know that from the unit circle, right? So the projection now of F onto V is going to be equal to, we already know this, the projection of F onto V is equal to F dot V over the magnitude of V squared times V. All these are vectors, so we want to put our little harpoon hat over top of them. It's what it reminds me of, right? Is a harpoon. It's just got that one hook. I don't know. It's just me. So now that we have our vectors written out, we can go ahead and do that dot product. When we do that, we're going to have 0, comma, negative 200 dotted with square root of 3 over 2, comma 1/2 over the magnitude of the square root of 3 over 2, comma 1/2, that quantity squared, times the vector square root of 3 over 2, comma 1/2. So notice here, our denominator, when we go ahead and calculate it out, the magnitude of this out, it's just going to be cosine squared plus sine squared, right? Well, that's going to be equal to 1 squared. And 1 squared, last time I checked, is just 1, right? Right, so our denominator automatically becomes 1. We don't need to worry about it. And our numerator, well, we're going to have 0 times the square root of 3 over 2. Well, that's going to be 0. So this whole fraction is just going to become negative 200 times 1/2. That's all the fraction becomes. And then we multiply that with this last bit here. So let's do that. What we've got then is negative 200 times 1/2 times the vector square root of 3 over 2, comma 1/2, which is equal to 100 times cosine of 30, sine of 30, and I'm out of room. I'll write that over here, which is going to be equal to negative 100 times square root of 3 over 2, comma 1/2. So that's what we just found F1 to be, right? All of this was F1. So that means the answer to this second part is just the negative of that. So all we have to do is flip the sign on 100 and we're good. Solid, done, don't worry about that part anymore, right? So, this whole part is equal to the negative of F1 which is going to be equal to 100 times all of this, or bringing it inside of our brackets, we're going to have 100 times the square root of 3 over 2, so just 50 times the square root of 3, and then 100 divided by 2, so just 50. So we're done with the second part. Now there's a reason why I went ahead and expanded this out, why I reduced this all the way down. The reason why is because sometimes WebAssign, whatever the homework website's called, WebAssign, right? I think that's WebAssign. I'm gonna go with it. WebAssign sometimes wants your homework put in this form. So I just went ahead and wrote it out that way. But you would be correct if you just wrote 100 times the square root of 3 over 2, comma, negative 1 over 2. Now it's important to notice this vector is not equal to this vector. This is in the opposite direction, right? This is in the opposite direction and reduced. What I did was I said negative F1 is equal to negative 1 times the vector 100 times square root of 3 over 2, comma, 1/2. Well, these negatives are going to cancel, so we have just 100 times the square root of 3 over 2, comma, 1/2. So now we're going to multiply that 100 through. Which is equal to 50 times the square root of 3, comma 50. That's where this comes from. Again, it is in the opposite direction of the projection of our force. And the reason why it is because it has to be the force equal to and opposite of whatever the force is pushing it down, right? And that force happens to be the projection of F onto our vector V. Okay, that was a lot, just for the first part. But the first part sets up the second part to be pretty quick. Now, notice from all of this, what we've got here, if we were to look just at this part right here, let me take that back. Notice that we solved for F1. That's where we should start. When we solved for F1, what we found was a vector, a unit vector, right? With a magnitude of negative 100. So the magnitude of F1 is negative 100. So we already know a huge chunk of what we need to know, right? Because work is equal to the magnitude of the projection of our force onto V times the magnitude of whatever our vector is, right? So we know our vector is in the direction of V. And we know that the projection of our force onto it is going to be 100, negative 100. Okay, cool. That means then what we've got is 3,000 is equal to 100, negative 100, my mistake. No, just 100, times the magnitude of our vector u. All right, the absolute value of negative 100 is just 100. So we can go ahead and drop the absolute values. Now all we have to do is divide straight across, right? So what we find then is that the magnitude of u is equal to 30. But the magnitude, but u is in the direction of v. So if we want to find out what u is, it's just going to be 30 times v. That's it. That's all this is. So u is equal to 30 times v, which is equal to 30 times the magnitude, or I mean the vector, square root of 3 over 2, comma, 1/2. And that's it. I know this seems like a lot, but really, I slowed this down a lot just to get to explain everything to y'all. So this first part, we found the projection of our force in the direction of V. We used that to find out what we had to have as a cancellation force, right? Like that cart's moving down the hill with a force of F1. We've got to push up the hill with a force of F1 in the opposite direction, so negative F1, right? To keep the cart from moving. But if we were to allow the cart to roll, it would have to roll 30 units before it did a work of 3,000. And that's what we just found out. So, having said that, let's look at another problem. And let's look at it piece by piece so that it's a little bit more clear. So, if I don't see a note on Rate My Professor about my amazing drawings, I am failing all of y'all because this thing belongs in MoMA, I swear. And no, I'm like the next Michelangelo. Okay, maybe not, but I am dope at math. And in this next example, what we've got is a barn door being pulled shut, right? And Dude Buddy McGee over here, the guy who's shutting this barn door, has a rope that's being held at an angle of 60 degrees from the top of the door, right? So the door's got this top, and Dude Buddy's holding it at an angle so that the angle between the rope and the top of the barn door is 60 degrees. He's pulling it shut. He's walking back 12 feet. Well, notice these are vectors, so we can move them around. So long as we don't change their direction, we can move them around anywhere. So notice that what we've got is the force F along that rope projecting along the top of the door, right? And we want to know the work done here. Well, we know he walked 12 feet. That's the magnitude. So it makes sense that the formula we're going to want to use here is going to be the magnitude of the projection of F onto U times the magnitude of U. We already know the magnitude of U. So we have to find out what the projection of our force onto U is. But before we go there, I want to point something out. Notice when we work all of this out, when we start working out the projection and then find the magnitude of the projection, something funny happens in the math. In this first bit, we can break up the fraction this way, right? Yeah, we were talking about that last class. We could break it up so that we have a unit vector times some value, right? Well, wasn't that a property of vectors? That we could just pull out that value, right? And then what we end up with is that the magnitude of this vector is just going to be the magnitude of the vector times whatever that scalar was. Well, it's a unit vector, so the magnitude's 1. So what we end up with then is 1 times the absolute value of that scalar. But hey, wait a minute. Didn't we also have something about dot products? Didn't we say we could rewrite it in terms of cosine? Yeah, we did. We said we could rewrite dot products using the magnitude of our vectors and a cosine of the angle between them, right? So u dot f, we can rewrite that as the magnitude of u times the magnitude of f times the cosine of 60 degrees. All of that divided by the magnitude of u. Well, hey, that cancels and that cancels. So all we're left with is the magnitude of f times the cosine of 60, absolute value of all that. But that's positive and that's positive, so I can just drop absolute values. And what we get is that all of this is going to be equal to the absolute value of our force, the magnitude of our force times cosine of 60 degrees. Well, I forgot to draw in what the magnitude of our force was. But the force has a magnitude of 50 pounds. So what we end up with is going to be the force times the magnitude of the force times the magnitude of u times the cosine of 60 degrees, which is equal to 50 times 12 times 1/2, which is equal to 300. Okay, so I went about showing this the long way. Now I'm going to go about it the short way. So we just said that the work is equal to 300. It's actually 300 foot-pounds is what it comes out to be. The units matter, but I'm not going to get into that just yet. So the other way of doing this is to recall that, hey, work is also equal to F dot U. Well, now by that same formula, this is going to be the magnitude of F times the magnitude of U times the cosine of 60 degrees. So that means we're going to end up with 50 times 12 times 1/2, and it's still going to be 300. So the reason why this comes out to be foot-pounds, like I started to say, is if we look at what we've got, we're pulling with pounds. The units don't disappear here. We're pulling a total of 12 feet. The units don't disappear here. So this is going to come out to be foot-pounds. Foot-pounds. So I know these are a little cumbersome, a little tedious, but the whole idea here is that we've got two different forms for projection. For work. We have two different forms for calculating work. You can say that work is equal to the magnitude of the projection of the vector F onto the vector along our distance, right? Times the magnitude of our distance, or I mean the magnitude of how far we walk, right? So the distance. Or we can say that work's not a vector. Why did I write the arrow over it? Or work is equal to force dot the vector with which we move along. And we also had that cosine of the angle between our vectors is equal to the dot product of our vectors divided by the product of their magnitudes we also had that the projection of a vector u onto v is equal to the dot product of u and v divided by the magnitude of v squared times v. So in this problem, we used all of these. And that was the real point of it, right? Was to kind of review these. If you have any questions, by all means, please shoot me an email. I know that this stuff is far from easy to work with, certainly not this part of the semester. It's certainly not online. So if you have any questions, shoot me an email. As many of y'all have discovered, and I've said a couple times now, I do not check my emails on the weekends. That is my time to work on my stuff. If you are waiting until the weekends to email me, don't. If you're waiting until the weekends to look at your homework, don't. Those are bad study habits, things that moving forward work on to fix. What I would suggest to everybody is you look at the homework at the very beginning of the week, try to get an idea of what you do and don't need help with. Watch the lecture videos ahead of time. That way you can figure out what you have questions for Thursday night at the latest. I can get back to you before Friday night, before the end of Friday night. You're pretty much after about 9:30 Friday nights. My computer's off. Having said that, anyhow, having said all that, have a good one, guys.